Hello and welcome everyone. Thanks for joining me today. I'm Benjamin, part of the technical and engineering team at Ventuer. My own background is in architectural design and building science, and I've spent more than 2 decades working across commercial buildings, design-intensive projects, complex facades, and some unusual projects that sat right on the boundary between architecture and hard engineering. Today we're going to look at ventilation and acoustic louvers, specifically in building facades, and why their performance has become a much more important engineering consideration in modern buildings than many people realize. Ventuer is involved in a wide range of facade and ventilation projects, and while I'll reference our work from time to time, this session is really about helping you understand why facade louvers are more than just a visual element. How airflow, rain defense, structure, and acoustics interact. What performance testing actually tells you and what it doesn't, and how louvers are engineered, tested, and integrated into modern facades. If you work in architecture, mechanical engineering, facade design, building services, asset management, or construction, this session is designed to give you a solid technical grounding, the kind that helps you make decisions with confidence, push back when something doesn't add up, and recognize where risk really sits. We'll start by stepping back and looking at the role louvers play in building facades. Facade louvers sit at a very specific boundary. They're part of the external envelope, exposed to wind, rain, and weather, but they're also directly connected to internal mechanical systems and occupied spaces. In most buildings, ventilation louvers are required to allow large volumes of air in or out, protect the building from wind-driven rain, contribute to the acoustic performance of the facade, and remain structurally stable under wind loads. At the same time, they're often located in highly visible or noise-sensitive parts of a building, near offices and apartments, and integral to plant rooms adjacent to occupied spaces or public areas. This means a louver is really just a hole with blades in it. It's a component that must balance multiple, sometimes competing performance requirements. So let's break down the 3 core engineering demands that louvers in a facade have to satisfy. The first requirement is stopping wind-driven rain. In real weather events, rain doesn't fall vertically. Wind gives droplets horizontal momentum. So even if the air turns, the water tends to keep moving in a straight line until it hits something. That's why blade geometry, spacing, and depth matter. A well-designed louver forces the airflow to change direction sharply. The air can turn, the water can't. So droplets impact the blades instead of passing through. Once water hits the blades, it needs a controlled drainage path to the exterior. This behavior is measured using wind-driven rain tests such as BSEN 13030, ASNZS 4740, or AMCA 500L, which we'll come back to later. The challenge is always the same: stop water without killing airflow. The second requirement is airflow performance. Ventilation systems are designed around specific air volumes and pressure limits. Every component added to the system, including the louver, increases resistance. Pressure drop rises quickly as air velocity increases, and it's strongly influenced by blade shape, free area, turbulence, and the number of directional changes the air is forced to make. Sharp edges, tight spacing, and complex geometries all increase losses. If the pressure drop is too high, fans work harder, energy consumption increases, and the system may fail to deliver the required airflow. So louver selection has a direct impact on system efficiency and economics, not just facade appearance. The third requirement is structural. A louver is still part of the facade and must resist both positive and negative wind pressures. On taller buildings or exposed sites, these pressures can be significant. Blades, frames, mullions, and fixings all need to be engineered to resist those loads without excessive deflection. Too much movement leads to rattling or vibration, noise generation, water ingress, or long-term fatigue issues. So the entire louver assembly must behave as a stable, predictable structural component. The challenge is that these three requirements don't naturally align. Improve rain defense and airflow usually gets worse. Improve airflow and water penetration often increases. Strengthen blades and pressure drop tends to rise. Designing a high-performance louver is about finding the right balance between these competing demands. That's why appearance alone tells you very little about how a louver will actually perform. Understanding performance testing is helpful because louver performance isn't intuitive. Two louvers that look very similar can perform very differently once tested. The three main wind-driven rain standards you'll encounter are AS-NZS 4740, BS-EN 13030, and AMCA 500L. They all test broadly the same things: water penetration at specified rainfall rate and externally applied wind speed over a range of intake velocities, and pressure drop measured in pascals over the same range of wind speeds plus the additional layers of intake velocities. The difference between the standards are mainly in process rigor, documentation, and whether extended testing is included. For many facade applications, airflow and rain defense are only part of the story. Ventilation openings are often weak points in the acoustic envelope. Noise can travel from plant rooms to occupied spaces, from the exterior into the building, or from internal spaces to neighbouring properties. Acoustic louvers introduce additional complexity. They typically use deeper blade profiles, absorptive infill or splitters. These features improve sound attenuation, but also increase pressure drop and affect rain behaviour. As with everything else, acoustics is a balancing act. Attenuation versus airflow, depth versus facade integration, absorption versus maintenance and weather exposure. A tested louver gives us a baseline, but real buildings add complexity. Wind conditions vary with height and terrain. Facade geometry alters airflow and water behaviour. Duct transitions, screens, and wall depth all change performance. That's why project-specific engineering is important. We typically review four main areas: structural design, applying actual design wind pressures from your local engineering codes and checking deflection, fixings, and stability. In New Zealand and Australia, the primary design standard for this is AS-NZS 1170.2. However, each country has its own relevant standard. Weather tightness, assessing how real facade geometry affects rain behaviour and drainage. Airflow performance, confirming true system pressure drop, including all downstream effects. And acoustic and wind-induced noise, reviewing potential for resonance, vibration, or noise generation under real wind conditions. Up to this point, we've talked a lot about louver performance in isolation. How blades handle rain, how pressure drop is measured, and how products behave under test conditions. But one of the most important performance factors doesn't sit with the louver itself. It relies on how the louver is integrated into the facade. What you're seeing here is Ventuer's glazed-in louver frame system. Instead of treating the louver as a penetrative opening through the facade, it's installed in the same way as an IGU would be. The louver is mounted within the aluminium joinery frame like an IGU, with glazing beads and wedge gaskets. From the curtain wall or window joinery perspective, its install is just like a glazed unit. That changes the problem fundamentally. The key innovation here is treating the louver like a window, not a hole. That has implications for weather tightness, coordination, scope boundaries, and installation quality. Installing a louver as a glazed-in element delivers several important benefits. Firstly, it improves weather tightness. Instead of relying on site-formed flashings, sealants, or secondary interfaces, the weather seal occurs where the facade system already performs best, at the glazing interface. Drainage paths, pressure equalization, and tolerances are already well understood and controlled. Secondly, it simplifies detailing and coordination. The louver becomes part of the window or curtain wall package, rather than a separate facade penetration that reduces the number of trade interfaces, clarifies responsibility, and significantly lowers installation risk. Thirdly, it improves buildability and consistency because the installation methodology is standardized. The outcome is far less dependent on site workmanship. The same approach can be applied across different Louvre models and blade depths by adjusting the frame depth, not reinventing the detail. And finally, it helps align ventilation openings with the broader facade performance objectives, particularly around air leakage control, water management, and long-term durability. In practical terms, this approach recognizes that louvers don't just need to perform aerodynamically, they need to perform as part of the facade system as a whole. Now let's discuss louver plenums and managing water that passes beyond the louver blades. Up to this point, we've focused on how louver blades stop wind-driven rain, but even the highest performing blade systems will allow a small amount of moisture to pass through under extreme conditions. That's normal and expected in performance testing. The critical question is what happens to that water once it passes the blades. This is where plenum design becomes essential. A plenum is not just an air transition box connecting a louver to ductwork. It is part of the building's water management strategy. If poorly designed, a plenum can trap water, allow internal migration towards ductwork, create leakage paths into the facade, or rely excessively on sealant and site workmanship. A well-designed plenum ensures that any water entering the rear of the louver is collected, directed, and safely drained back to the exterior. In other words, blade performance and drainage performance must work together as a single system. A plenum is critical when a louver connects to ductwork. Its function is to distribute airflow evenly across the louver face, manage pressure drop, control water drainage, and reduce noise. Poor plenum design leads to uneven airflow, reduced ventilation efficiency, water ingress, and noise issues. This is a fully welded integrated aluminium plenum, factory fitted to the louver and designed so that any water that makes its way through the blades is drained back externally. The engineering significance is that it eliminates site-sealed box interfaces, controls internal water migration, reduces reliance on site workmanship, and maintains predictable airflow transition. This is essentially a performance-controlled, factory-resolved solution. What we are looking at here is Ventuer's proprietary plenum adapter profile. It's a factory-fitted adaptive profile that is fixed to the rear of the louver, allowing a secondary plenum to be attached on site, ensuring correct plenum height and alignment, and providing sealing interface control. This is clever because instead of supplying a fully welded plenum every time, which increases freight, cost, and rigidity, the adapter standardizes the interface geometry, controls sealing location, maintains drainage plane continuity, reduces installation error risk, and preserves flexibility for site-fabricated plenums. From an engineering and commercial standpoint, this is a useful innovation. Instead of leaving coordination between facade contractor and mechanical contractor unresolved, the adapter formalizes that boundary. From a water management perspective, it ensures the drainage path remains aligned with the facade strategy. From an installation perspective, it improves repeatability and reduces ambiguity around responsibility. In practical terms, it recognizes that preventing water ingress is not just about blade geometry, it's about managing every interface between the louver as part of the facade system. The key technical advantage that comes from these interface details are controlled transitions from free airflow to ducted flow, improved static pressure distribution across blade height, and reduced turbulence at the louver throat. When specifying louver systems for building facades, the choice of finish is not just an aesthetic decision. It also plays a critical role in long-term durability and maintenance performance. There are several types of coating systems commonly used on aluminium louvers, and understanding the difference between them helps ensure the finish aligns with the environmental exposure and design life of the building. The most common option is polyester powder coating, which is widely used across facade applications. Within this category, there are different performance grades. Standard architectural grade polyesters, such as Dulux Duralloy or Interpon D1010, are typically suited to lower exposure environments or less critical applications. They provide a consistent finish but have more limited resistance to UV degradation and color fade over time. For higher performance applications, durable polyester systems such as Dulux Duratec or Interpon D2525 are often specified. These coatings offer improved resistance to UV exposure, better color retention, and are more appropriate for exposed facades where long-term appearance is important. Beyond polyester systems, fluoropolymer powder coatings represent a further step up in performance. Products such as Dulux Fluoroset or Interpon D3020 Fluoromax are designed for highly exposed environments and offer superior resistance to UV degradation, chalking, and color fade. These coatings are often used on premium facade elements or in coastal and high UV environments, where durability expectations are higher. Another alternative to powder coating is anodizing, which is an electrochemical process rather than an applied coating. Anodizing converts the surface of the aluminium into a durable oxide layer, providing excellent corrosion resistance and a distinctive metallic finish. Typical anodizing thickness includes 12 micron, which is generally used for interior or lower exposure applications, and 25 micron, which is more suitable for external facades in harsher environments. Anodized finishes can be provided in natural silver or a range of colored finishes, depending on the architectural intent. Each of these systems has different performance characteristics, and the appropriate selection depends on factors such as environmental exposure, facade orientation, maintenance expectations, and desired lifespan. In practice, aligning the coating specification with the overall facade durability strategy ensures that louver systems not only perform functionally, but also maintain their visual integration with the building over time. It's also important to consider galvanic corrosion. This occurs when dissimilar metals come into contact in the presence of moisture. Because louvers are often aluminium, but may connect to steel structures, stainless fixings, or galvanized supports, material compatibility becomes important. If incompatible metals are connected without isolation, corrosion can occur over time. Typical mitigation strategies include isolating washers, compatible fasteners, protective coatings, and careful detailing. These are small design decisions that can have a significant impact on long-term durability. In some facade applications, louvers are not only required to provide ventilation, they also need to control line of sight and light transmission. This typically arises where plant rooms, car park interiors, or service areas sit directly behind the facade, and there is a desire to limit visibility into those spaces or reduce light spill, particularly at night. From a design perspective, there are two primary approaches to solving this. The first is to invert the louver blades. This can be effective with a single bank louver blade like the VL100CM. By reversing the blade orientation, the direct line of sight through the louver can be significantly reduced or eliminated while still maintaining airflow. However, this approach comes with an important limitation. Inverted blades generally reduce the louver's ability to manage water ingress, as the blade geometry is no longer optimized for shedding wind-driven rain. As a result, this solution is typically only appropriate in situations where water penetration is not a critical concern, such as rooftop, plant screens, or sheltered facade zones. The second approach is to use a multi-stage louver system with dual or three-stage configurations. These systems introduce additional blade layers or opposing blade orientations, which break up the line of sight while maintaining a controlled drainage path through the louver. Because the airflow path is more complex, multi-stage louvers are able to provide visual screening and improved weather performance, making them suitable for exposed facades where water ingress must be carefully managed. Understanding that trade-off early in the design process helps ensure that selected louver systems align with both the visual and environmental performance requirements of the facade. In seismic regions, facade systems must accommodate building movement without losing functionality. Curtain walls, windows, and cladding panels are typically designed with movement joints that allow the facade to shift during seismic events. Louvers installed within these systems must be able to accommodate the same movement. If they are too rigidly fixed, they can transfer loads back into the facade framing or experience deformation themselves. Good louver design therefore allows for tolerance and flexibility within the supporting frames so that the system can move with the facade without compromising performance. A related but separate issue is the movement between the facade and internal surfaces. Ductwork connected to facade louvers is often supported from the structure of the building, not from the facade. During seismic movement, the facade and the duct systems may move differently. If that movement is not accommodated, significant stress can be introduced at the connection between the louver plenum and the duct. Flexible connections, expansion joints, or adaptable plenum interfaces are typically used to allow this relative movement without transferring loads into the louver frame. This is a coordination issue between facade and mechanical engineers and is best addressed early in the design. An interesting property of aluminium louvers is their relative ductility compared with other facade materials. Glass panels, brittle claddings, and rigid facade systems tend to fail once the deformation limits are exceeded. Aluminium blade systems, by contrast, are relatively flexible. They can absorb and redistribute loads without immediate failure, particularly under dynamic wind conditions. This ductility can be beneficial in both seismic and high wind environments, provided the system is properly engineered and supported. The key point is that louvers behave differently from solid facade materials, and that behavior needs to be considered during design. Modern facades increasingly use perforated metal as part of the architectural design language. Architects often specify perforated aluminium panels to screen plant areas, conceal surfaces, or create textured facade zones that interact with light and shadow. A challenge arises when those perforated surfaces need to accommodate ventilation openings. Traditional louvers with solid blades and visible depth can interrupt the visual rhythm of the facade and immediately reveal the location of plant rooms or mechanical spaces. A louver panel with a perforated screen that conceals the blades offers a way to resolve that conflict by introducing an element that ties in with a facade. The ventilation system can maintain the airflow required by the mechanical design while visually integrating with the surrounding facade panels. Ventuer's VL50PL louver was developed with this challenge in mind. The system allows perforated panels to be incorporated over the louver blades, maintaining an aerodynamic geometry for airflow while presenting a perforated outer surface that aligns visually with the surrounding facade. The VL50PL is available with 6 different perforation panel patterns, allowing the louver to match a perforated facade used elsewhere on the building envelope. This gives an architect flexibility to align hole size, spacing, and visual density with the broader facade design, rather than forcing the ventilation opening to appear as a separate element. In practical terms, this means the louver can wear the same shirt is the rest of the facade. From a distance, the ventilation opening reads as part of the architectural surface rather than as a mechanical interruption. The result is that large ventilation openings, which are often unavoidable in plant rooms, data facilities and service floors, can visually disappear into the facade while still delivering the airflow performance required by the building services design. Any lightweight facade component exposed to airflow can experience wind-induced vibration. When air flows across blades, small pressure fluctuations can develop. Under certain conditions, these can excite vibration in the blade or frame. Over long periods, repeated vibration can cause fatigue in metal components or fixings. This is particularly relevant in high wind environments or on tall buildings. Proper blade stiffness, secure fixings, and appropriate structural design all play a role in preventing these issues. In some cases, wind tunnel testing or detailed engineering review may be used to assess vibration behavior. Another real-world issue is how water from the facade above interacts with the louver. Rainwater running down glazing, cladding panels, or parapets can concentrate and discharge directly onto the louver. If this water flow is not considered, the louver may receive far greater water volumes than those simulated in laboratory testing. Architectural features such as flashings, drip edges, or overhangs can help redirect this water away from ventilation openings. Considering the watershed above, the louver is an important part of facade detailing. Installation methodology is an aspect of facade ventilation systems that is often considered relatively late in the design process. However, in practice, it can have a major influence on the performance, durability, and construction efficiency of louver systems. Modern construction is increasingly moving towards prefabrication and modular installation. Where possible, louver systems can be manufactured and factory assembled into modules that arrive on site ready to install within prepared facade openings. This approach improves quality control, reduces installation time, and minimizes the number of site-formed joints, which are often the most vulnerable points in any facade assembly. Factory fabrication also allows better control over tolerances, sealing, and drainage components such as plenum assemblies or flashings. These details can be carefully integrated during manufacturing rather than being assembled under variable site conditions. However, achieving these benefits often depends on engaging with suppliers and specialist contractors early in the design process. Louver systems sit at the intersection of several disciplines. They connect to the facade system, interface with structural framing, and often link directly to mechanical ductwork within the building. Because of this, their final configuration is influenced by architectural intent, structural constraints, mechanical airflow requirements, and practical installation considerations. Early supplier engagement allows these competing requirements to be coordinated before the design becomes fixed. For example, manufacturers can advise on practical module sizes that suit fabrication, transport limitations, and safe installation methods. They can also highlight where drainage, plenum design, or fixing strategies may require additional space within the facade build-up. Similarly, discussing installation methodology, discussing it early, can help identify opportunities for prefabricated assemblies, simplified fixing strategies, or modular louver sections that align with facade panelization. This type of coordination can reduce installation risk, shorten construction programs, and avoid late-stage redesign when site constraints become apparent. In essence, thinking about installation methodology early allows the project team to align design intent, manufacturing capability, and site installation methods so that the louver system performs as intended once the building is complete. Early engagement drives success. From the outset, Ventuer was brought into the Pikaha project in September 2021, 2 years before installation commenced. This early involvement allowed us to work alongside architects, engineers and contractors to shape the design, troubleshoot complex junctions and ensure our products would integrate seamlessly. Engaging suppliers early ensures that design decisions are practical, achievable and fully engineered, reducing costly on-site changes and enabling confident coordination with other trades. Collaborative design and custom engineering. Every panel, actuator and blade was reviewed in the early stages to ensure both performance and aesthetic requirements were met. For example, custom rotary actuators were designed to handle forces that linear actuators could not, while still maintaining precise control of blade movement. Early testing of tolerances, lever arms and torque requirements allowed the project team to avoid potential issues with large 500 kg panels and complex structural interfaces later on. Installation strategy and mock-ups. Planning for installation began long before the first panel was fabricated. Mock-ups of critical facade sections enabled site teams to trial methods for handling oversized panels, verify waterproofing junctions, and refine sequence logistics. Custom handling frames, pre-notched flanges, and two-part waterproofing plugs were all pre-engineered to simplify installation and reduce risk. By pre-fitting EPDM tapes and modular components in the factory, we minimized site labor and ensured consistency across 1,000 square meters of Louvre panels. Integration with other trades. With multiple contractors working on cladding, windows and structural steel simultaneously, early supplier engagement allowed us to coordinate interfaces. Details such as the two-part flashing system to allow seismic movement or pre-notched louver flanges around well plates were resolved before arriving on site. This proactive approach prevented delays, avoided damage to completed works, and ensured aesthetic alignment with the cultural facade design. Optimizing safety and efficiency. The early collaboration also extended to lifting and rigging methods. Large panels required engineered lifting frames and careful planning to access complex exterior areas safely. By resolving these requirements early, the installation team could work efficiently without relying on interior scaffolding or compromising safety. The key takeaways are that early supplier engagement ensures design feasibility and reduces risk on site. Collaborative engineering allows standard products to perform in unique and complex applications, and factory pre-assembly and modular components streamline installation, even for large, heavy panels. Coordination with all trades before installation improves quality, efficiency, and safety. To support designers early in the process, Ventuer provides a couple of tools to assist in preliminary Louvre specification. Our Louvre selection software allows comparison of airflow, pressure drop, rain defense class, and free area. And a Louvre calculator used in early design to estimate required opening sizes, face velocities, and pressure losses. These tools are based on tested performance data and reflect the same principles we use internally. They don't replace project-specific engineering, but they make early decisions faster and more reliable. In conclusion, the purpose of this webinar has been to give you a clear technical understanding of how ventilation and acoustic louvers function as engineered facade components, not just catalogue items. The key takeaway is that Louvre performance affects energy efficiency, acoustic comfort, facade durability, and system reliability. Ventilation openings are amongst the most exposed and performance-critical parts of the building. Treating them as commodity items introduces unnecessary risk. By understanding the engineering principles, testing methods, and real-world performance considerations, you can make better informed decisions and deliver facades that perform as intended.